In this video, we're going to look at some of the applications of finding a vertex in a quadratic function. So the main reason that it's helpful to know how to find the vertex is because the vertex represents a minimum or a maximum point. So in any situation that can be modeled with a quadratic equation, and there's a bunch, a quadratic function, sorry. So trajectories, area problems, revenue problems, there's a number of different ones. We'll look at a couple in this video. If we're wanting to find a maximum or a minimum, we're wanting to find the vertex. So very simply, this one's not really necessarily a real life application, but just to kind of get started, if we know we have two numbers that have a sum of 75, we want to know their maximum possible product. So you can start this just with one variable. I'm going to do it with two variables, so I'm going to let A and B be the numbers. So let A and B be the numbers. Always start by defining your variables just so we know what we're dealing with if you're using X and Y, or if you're just doing this using a single variable, which is entirely possible. We need to make sure that everybody following your work knows what you're referring to. So now I have two sentences, and each sentence basically helps me find an equation. So two numbers have a sum of 75. So A plus B equals 75. I'm looking for the maximum possible product, which means I need a function for the product. So whatever it is I'm looking to maximize or minimize, that is the thing I need a function for. So in other words, that's basically the y value of my function. So their product is A times B, just by definition. Now, this is basically a function that has three variables. Product is a function of A and B. So I'm going to use the first equation to substitute in so that I have a function with just two variables. The product equals some function of A or B. So let's isolate A, and that means I have A equals 75 minus B, which is what I can substitute in here. So the product is 75 minus B times B. This is quadratic. I could distribute it if I wanted to. That's actually not going to be helpful for what I'm trying to do, but in some situations it would be. So if I were to distribute it, I would have this quadratic function, which we would more commonly write in this way, in which I can see pretty clearly it opens downward because I have a negative leading coefficient. But there's no point in distributing right now because I have it in the factored form, which means I have it in the form where I can see the x-intercepts. So in other words, if B equals 75, or if B equals 0, so these are the two factors, then P will be 0. So that's, sorry, I had a weird little jump happen on my screen. Then P equals 0. Now, that's not what I'm looking for. I'm not looking for when is the product 0. And in fact, because there's nothing that says these numbers have to be positive, that's not even the minimum possible product. The minimum possible product is something, well, there isn't one because this carries on infinitely in the negative direction. So the minimum possible product doesn't exist. Negative 7 million is a possible product, and also numbers less than that. But what that tells me is that graphically, I have something that looks like this. So the vertex, which is what I'm looking for, has to be halfway between 0 and 75. So now that I know where the product is equal to 0, what I know is that the maximum occurs is at the point where B is exactly halfway between those two. So 75 over 2 or 37.5 if you prefer in decimal form. So that is when the maximum product occurs. I didn't ask what the numbers are when the maximum product occurs, although if I then wanted to figure out, I could then say A also would actually in this case have to be 37.5 because A is 75 minus 37.5. But again, I didn't ask what the numbers were. I asked, what is their maximum possible product? So the maximum possible product is what I get when I actually use these two numbers and multiply them together. So in other words, what is 37.5 times 37.5, or 37.5 squared if you're paying attention? And that gives me a maximum possible product of 1406.25. So in other words, if I have two numbers that have a sum of 75, the highest product I can possibly create for those two numbers is 1406.25. So that would be the coordinates here would be 37.5, 1406.25. Those would be the coordinates of that vertex. And the part of the vertex that answers the question is the y value, or the p value in this case. What is the maximum possible product? Now, looking at an example that's a little more contextualized, let's say we have a farmer who has 40 meters of fencing and they want to enclose a rectangular pasture. So they want to create some sort of field that is in the shape of a rectangle, and they want the maximum area. Now, notice the question doesn't ask what is the maximum area. Sometimes it might. What it asks is what dimensions will give the maximum area. So at the end, I have to make sure I'm actually answering that question. So I'm looking for maximum area, though, which I said above means I need a function for area. So area basically is length times width. We know that, or base times height, depending on how you want to show it. I'm actually going to use base and height because then my L doesn't look like a 1. Where in my rectangle, let's say that is B and that is H. I don't have to write a sentence defining these variables if I'm sketching them on a diagram. It's clear from my diagram now. B and H are the dimensions of a rectangle. So I want maximum area. I need a function for area. But just like in the previous case, this is an equation with 3 variables. I don't want 3 variables. I only want 2. So I need to use the other information. He has 40 meters of fencing total to enclose the pasture. Well, that's perimeter. So this means that 2b plus 2h equals 40, which I can divide by 2. That means that b plus h equals 20. And isolating either one of those variables, let's say b equals 20 minus h. So now this actually is just like the previous question. I have two numbers with a sum of 20, and I want to maximize their product. It's exactly the same question I just had. So substituting in, I've got 20 minus h times h for the area. This means, as in the previous case, that if h equals 20 or h equals 0, then the area would be 0. That would be nonsensical in this context. That would basically mean that the farmer created a line of fencing. He did 20 meters of fencing in one direction, turned around, doubled it over itself, and did 20 meters of fencing in the other direction. That would actually, in this case, be the minimum possible area. He could create a collapsed rectangle that has 0 area. There's no point to do that. In this context, b and h cannot be negative. So my parabola doesn't continue on infinitely. In the previous case, when I sketched it, I drew arrows. But in this case, if I wanted to sketch it, I would actually have to stop. That's 20. That's 0. It doesn't exist anywhere else. But the important part to note is that the maximum will occur in the middle. So the maximum is going to occur when h equals 10. So max at h equals 10. So this is the point 10 something, whatever that area is when the h is equal to 10. I don't care what the maximum area here is, so I don't even have to calculate that. I just care about the maximum dimensions. So h equals 10, that means b equals 20 minus 10, which is also 10. So the maximum dimensions are 10 meters by 10 meters. Now it's actually pretty obvious the maximum area would be 100. So the maximum actually occurs when that rectangle is a square. That will always be the case. For a fixed perimeter, the maximum rectangular area you can create is actually by making it into a square. The maximum overall area you can create is by making it into a circle, but that's a very rare shape that we would use. So square is a type of rectangle. Knowing that it's always going to be a square, we tend to create some sorts of conditions here. So maybe he only needs to enclose 3 sides because the 4th side of the rectangle is against a wall or something like that. That's going to change the fact that it's not always going to be a square. So for example, let's say we still have that same farmer with 40 meters of fencing, but this time they want to enclose 2 adjacent rectangular fields. So in other words, adjacent means touching. So I have 2 fields like this. It doesn't actually matter if those two fields are equal or not. So whether this line in the middle is exactly in the middle or just off to the side here doesn't change the overall total area of the pastures, and it doesn't change the total amount of fence used. But in this case, I actually have something different. I still am trying to maximize area, so I still need the overall base and height of this rectangle because I want the overall total area of the two fields. But what's important to note now is that it's not going to be b plus h equals 20, because now I'm using 40 meters of fencing to do a little bit more. Now what I have is that 2b plus 3h equals 40. So this gets a little more complex, but I still do the exact same thing. Let's do this as 2b equals 40 minus 3h, which means b equals 20 minus 3 over 2h. This means that the area is 20 minus 3 over 2h times h. Still factored form, so it's still relatively easy to find my maximum. The x-intercepts are going to be, well, this one's a little trickier to find, but I'm wondering when this equals 0 or when h equals 0. So when does 20 equal 3 over 2h? Or in other words, when does h equal 40 over 3? Or h equals 0. So the max occurs exactly halfway between them. So in other words, 40 over 3 divided by 2. So the maximum occurs at h equals 20 over 3 meters. Now, again, I want to know what dimensions, so I need to figure out what b is for that. So 20 over 3 times 3 over 2 is going to be 10, and then 20 minus that, 10 meters. So the dimensions are going to be 20 over 3 meters. You could absolutely state this as a decimal, so I could give this as 6.67 meters, 3 significant digits. But now it's no longer a square, but that is what it would take to have the maximum area.